It says I'm muted. Okay, so the difficulty here is that we don't know exactly what these slopes are, right? We don't know if that's a slope 0.5 or is this a slope of -1/2, maybe that's -2. We really don't know. But we do know are the general things. So we can list out those information, right? We know where slope 0, we know what slope 0 looks like. We know what slope undefined looks like. Okay, we know what positive slope looks like. And we know what negative slope looks like. So we're going to look at this and see, do we see a collection of slope zeros gathered on this graph? And I don't think so, right? Sometimes these markings on the y-axis may be slope field segments, but sometimes they're not. So we can't really depend on that. So I'll put a question mark there. Maybe there is. Maybe it's being hidden behind the x-axis. Oh no, actually it's not, right? These are definitely slope segments. So, but sometimes it's hidden behind the x-axis that we can't see. So we'll put a question mark there. Okay. Okay. What about slope undefined? Yeah, when there's nothing there. Mm-hmm. Yeah, that's it. Cam, can you hear me?
I can hear you.
Okay, great. Okay, so Tam, we're on the slope fields worksheet from yesterday. We're doing 7 and 8. Okay. So you said y equals -1, right? Yeah, that's it, blank space. So that means if I plug y equals -1 into the differential equation, I must get it undefined, right? And that's something that we can use to eliminate the wrong choices. Okay, where do you see a collection of, or can you make some general observations in terms of where positive slopes occur?
There are a bunch in quadrant with 3.
Mm-hmm. Where else?
And quadrant 2.
Yeah, so basically all of quadrant 2 and 3, right? That's good.
X is negative.
Yeah, that's true, right? Whenever x is negative, we should get positive derivative. Okay, where do you see negative slope?
Well, the other half.
Mm-hmm.
Where x is greater than 0.
Mm-hmm. Yeah, whenever x is greater than 0, or dy dx should be less, should be negative. Right, so we have really good descriptions here. We should be able to eliminate some choices that we know are wrong. And we can't depend on slope 0, but slope undefined, right? Which one can we eliminate? Which one, if we replace -1 in for y, we're not getting slope undefined. If we're not getting slope undefined, we should be able to just cross it out.
Just plug the -1 column.
Mm-hmm.
The first one, wait, I always mix up which one is undefined and divided.
Okay, yeah, so undefined is something like this. It's like 4 over, if you have 0 in the denominator.
So then the first one would be
The first one would be okay, right? Because if I put -1 in for y, I get 0 in the denominator. So this is consistent.
Oh, I thought it was, okay,
Mm-hmm.
I thought we were marking off if it applied.
Oh, okay, yeah, if it applied, yeah, we can check it off. But right now, I think it's easier to eliminate the wrong ones. That way, we can just narrow down our choices.
And the one below that would be 1 and 0 is off.
Yeah, this one's off.
I'm sorry, I can't seem to find this problem on the website.
Okay, sorry, Cam, say it again.
I can't seem to find the website on the question on the website.
Oh, let's see. You don't know which worksheet this is from?
No.
Okay. Yeah, I'll post the that link. Okay, Tam, is that what you were hoping to find, the worksheet?
Yeah, it was. Thank you.
Okay. Yeah. Okay, so this one is definitely wrong, right? Because I put -1 in for y, I'm getting a 0 in the numerator, not 0 in the denominator. So we can't guarantee slope undefined every time y is -1 for this. What else? Okay, what about these two here?
Oh, wait. They both cancel out. Wouldn't they cancel out to 0?
Right, and 0 is not undefined.
Correct.
So this is obviously wrong as well. Because what we want to do is we need to be able to replace y with -1 and get undefined.
Oh, I
But-
thought okay, that makes. I thought you were saying it equaled 0, so couldn't it be sub 0? But it can't be sub 0 because there aren't lines there.
Right. So
Cross off the 2.
we can cross off these two because both of these will produce 0, but they're not producing undefined, which is what we want.
If
And
it produced 0 somewhere else, like the possible ones we had said, if that would have made sense.
right. But there aren't any. Right. So I think rather than looking for the right one, I like to look for the wrong ones, and then it'll make my process faster, I feel. But I think once we're down to this one, I think it's just good practice just to convince ourselves why this is the correct one. So let's go down the list. Okay. So it looks like there is a slope 0 when x is equal to 0. We just really couldn't tell. We couldn't really tell whether these were markings for the y values or whether these were markings of 0. But it looks like, if I put 0 in for x, I am getting, when x is equal to 0, that there is a slope 0. But we really didn't want to depend on that, right? Okay, so second option, slope undefined, that's true. If I put -1 in for y, I get 0 in the denominator, and it's all completely blank here. Positive slope in the second and third quadrant. Let's see. Negative. Yeah, that's right. When x is less than 0, right? When we get negative x values, that negative is getting canceled out with this negative, and it's forcing a positive out of those regions. The denominator has no say in this because the denominator is always positive, so it's really the numerator that's driving the sign of our slopes. Negative slopes, whenever x is greater than 0, right? So all these values when x is positive, it's staying positive, which the negative is going to take over. Negative or positive is negative, so it's causing all these negative slopes. So yeah, just further confirmation that we got the right one. Okay. All right, number 8. You want to spend a minute to try this one, and then we can go over it. Okay, I'm having you guys try these. I'm going to pause the screen for a moment. Mm-hmm.
So I see a bunch of like positive slopes, but like there's a gap of like negative. I don't know what this is.
Mm-hmm. Mm-hmm. Okay, so what are you thinking right now?
It goes positive, so it hits the x being -2 and then negative y.
Okay.
And then, oh wait, no. Wait, the ones in the quadrant 3, those are straight up and down. Those are negative.
Mm-hmm. Quadrant 3 is negative.
Oh, quadrant 1 and 2 are positive.
Yeah.
But those, what about the ones on the y-axis?
On the y-axis, those are positive. Right.
So anything above the.
Yeah, I think that's what I was looking at as well. Yeah, I think that dividing line of that x-axis is really separating the positive and negative slopes. So positive slopes, I think quadrant 1, quadrant 2, like what you were saying. Negative slope, quadrant 3 and 4. Slope undefined, I didn't really know. Yeah, well, I don't think there are any. I don't think there are any slope undefined. If there were vertical, yeah, I don't know if these are blank or whether these are markings for our values. So I didn't, and maybe at y equals 0, but I'm not really sure. Okay, but you have these other, okay. All right, so now let's go down our list. I like to look for wrong answers so I can eliminate them. So that means if I replace x with 1, I should always get a slope 0. Which one is obviously not right? Which one? Say it again? First one will be wrong. Well, if I put 1 in for x, I get 0 over y, and 0 over y is mostly 0.
I keep mixing up with
Undefined and 0. Yeah, so 0 slope is like 0 over 4, for instance. That's an example.
0 over 4 is slope 0.
Slope 0,
and
right.
4 over 0 would be
Slope undefined. That's right.
Okay.
Okay.
No, never mind. The first one.
So I think first one is still good, right? It's still in play. We'll leave it alone. How about the second one?
That one would be slope undefined.
This would be slope undefined. And we don't want slope undefined at 1, all right?
Correct. That's wrong.
So this is wrong. This is obviously wrong. Hey, how about the third one? X minus 1 over y squared.
That one can be slope 0.
Yeah, this one is still safe. So we'll leave that alone.
And then the last one, because it would have a 0 on the bottom.
Which is okay.
But now that.
Oh yeah, but that's right. You're right. Yeah, if I have 0 in the denominator, we don't want that. We want slope 0, so this one is out. Okay, so I think only first and third are in play. We'll skip the second property because we don't know exactly what's going on. But Okay, so we want positive slopes whenever y is positive. So that means if y is positive, I should always get a positive number. Do you see one that is obviously incorrect? Or if you're unsure about these general statements, you can always just test a point, right? Just pick a point.
Right now.
Okay, so which point do you choose?
I just picked 1, 1.
Okay, I wouldn't choose 1, 1.
Number, so it's more obvious.
Yeah, because 1, 1, it looks like slope 0, right? So pick a point that is obviously a positive slope.
I could do 5, 3, or 5.
Yeah, 5, 3, yeah, that works. So that means 5, 3 should give you positive. Okay, so maybe that one is not as obvious. Let's pick another one. Maybe pick another quadrant.
Wait,
Mm-hmm.
pick a point where the line is questionable about which way it's going.
Well, pick a point that you know is a specific a slope in terms of positive or negative.
What is negative 3, 4?
Negative 3, 4. Yeah, negative 3, 4. We know it should be positive, right? Because it's in the second quadrant. Okay, so let's put negative 3, 4 in. I think I get positive here. How about here? Yeah, this is negative, right? And that's not consistent. So I think our answer choice should be this first one, right? Okay. And looks like there is slope undefined at y equals 0. We just weren't really sure because of that x-axis. Okay, so if we go down the line here, we know that this is our answer. Okay, double check. If I put 0 in for, 1 in for x, I do get 0 in the numerator, so that is slope 0. Looks like there is a slope undefined at when y is 0. We just couldn't really tell, but it makes sense because we don't see any markings here except for what's marking the x values. Positive slope, whenever positive y value, we're getting a definitely positive. So it looks like the denominator is driving the sign of this derivative of the slope. The numerator is always positive. So whenever y is positive, we know that this overall slope is going to be positive. Whenever y is negative, we know this overall fraction is negative. So that's consistent with statements 3 and 4. Okay, any questions with slope fields? So yeah, I like this method of listing out things that we can tell, and then after we list it out, eliminate the wrong choices, and if you're down to 2, then start picking individual points where you may not know the exact slope value, but you know generally what slope it is in terms of positive and negative. Yeah. Okay, so let's look at worksheet 3. It says morning review at the top, but I figured that this would be a good place to do some practice integral problems, since I felt like I did a lot of differential equations yesterday, and those were recorded, and today we'll maybe do more of the integrals, and ones that, and I may create some additional ones that you don't see here. So this is number 4. I'll put it on a separate sheet. Okay, so if I go down my list of options here, denominator has too many terms. I know I'm not going to be able to move. I'm not going to be able to separate anything. Okay, so that option is out. What about U substitution? Is that a possibility? Okay, what could be our U value? Inside the parentheses. Yeah, let's start there. Okay. Maybe you're looking at the numerator going, what if that 2 is going to cause trouble? But you know that you can always factor the 2. But for the most part, e to the x is itself, so that is a pretty good sign that we should be able to produce a derivative that should look somewhat like the numerator. Not perfect, but that's a good place to start. Yeah. Yeah, and usually if I see parentheses, I see that as a helpful sign. That's something that kind of usually makes our process a little easier. But no guarantee. It's just a good place to start. Okay, so we can find the derivative. As you recall, the derivative for e to the u is just e to the u times u prime. So e to the x times 1, nothing's going to change here. But here, e to the negative x times negative 1, right? Negative x's derivative is negative 1. I'm not going to push that e down to the denominator because I'm always looking to see what I want to cancel out. So the more that I can make my derivative form look like what I want to cancel out, visually it'll be easier when I get to canceling out. So cross multiply here. No. Solve for dx. Make my substitutions. Okay, so we're close. All right, what can we do next? What do you guys think? Yeah, factor out the 2. That should help us see things a little more clearly. And then we have a match now, right? Okay. Push the 2 out in front. All right, where do we go from here? What rule do we use for that form? How do we handle 1 over u squared?
U goes to U. use the natural log.
Good. We can't use natural log, right? This is only reserved for u to the first power.
Would it be u to the n?
Okay? It's going to have to be power rule, right? But is this ready for power rule? What needs to happen?
U to make it U to
-2, yep. So we got to make that adjustment. I think a lot of students see this u in the denominator and they all assume that it's natural log, but it doesn't work with natural log, right? Think of this as the exception. This is the one rule that runs into a problem with power rule. So we have this special case. But most other exponents fits under the category of power rule. If it's in the denominator, we do need to make an adjustment. We do need to push it up to the top, and then we should be in the clear to apply power rule. Okay. Okay, so what's the antiderivative?
just be,
Mm-hmm.
just the negative 1 over negative 1.
Yep.
It should be negative u to the negative 1.
Right. Okay, we can do a little bit of cleanup. We can push the u back to the denominator. We can replace the u back in terms of x. Okay, any questions with 4? Okay, let's look at number 5. Anybody still need this? You guys good? All right, 5. Okay, negative sine x times 3 to the cosine of x dx. We see a rule that we can work towards. Not quite.
Would you start with the 3 cosine?
Yeah, those sine and cosine are kind of distracting. Those are kind of just side things. What's the main thing here?
The a to the u.
Yeah, that 3. That 3 indicates it's an exponential function in the form of a to the u. So that's going to be the best fit. Okay. Yeah, sometimes it's tough to see. But, anytime you see a number raised to a variable, that is, right, that's a red flag, right? We know that if we let the u value be anything else, that 3 is not going to go away. So we need to let that kind of be the, is helping us match a rule that we can use. Okay, so if we're trying to match with a to the u, then we know our a value is 3. We know that our exponent is going to be our u value. So this should work out because the derivative of cosine should produce something that will match that, and we should be able to get it to look like this rule here. Okay, so. Okay, so the derivative for cosine is negative sine, so it'll be on the formula sheet. I'll put that over here. Okay, and then the rule that we're working towards is this. perfect match, no coefficients. Looks like we can work towards our integral rule without having to keep track of any leftover coefficients. Okay, just do what the rule says.
Could you simplify it to 3% instead of,
Sure, you can divide these, which is fine. The danger that I see with this type of problem is if there was a coefficient, let's say if there's a 2 here, I think the tendency is a lot of students want to multiply the 2 and 3 together and make it 6. So just know that this is kind of stuck. If there's any coefficients, it has to stay separate from that base. We can't multiply any number into that base. I mean, we can, we just need we need a form like 3 to the u, but we're not going to get that. So just be careful. Any coefficients, this is going to have to be left alone. Okay. All right, I'm going to pick some problems that's not off of this. I think number 6 is more complicated than what you'll be seeing on the test. So, and then 7 we've seen already from yesterday. So let's do let me pick ones that we haven't done in a while. Are you guys okay with 5? Okay, right. All right, let's try this one here. No, it's not. So this is just a made up one here. So. Give you guys a minute to process this. Oh, let me add something to this. Let me make this. Make this with bounds.
Is something like the part where you just added one, would that be on the?
Right, we need to be able to do definite integrals, but we know that's always the last thing, right? That's always, we never worry about that at the beginning. Okay, so let's go down our options. Is this something that we can expand, separate into individual fractions? Yeah, that denominator is giving away, right? 2 terms, we know it's out. Well, let's move on to something else. Okay, next option, U substitution. Yeah, the exponents are not favorable for that situation, right? Okay.
Would you do the division?
Yeah, I think synthetic long division is going to be a good option because you see the numerator is greater than the denominator. I mean, they can be the same degree, but the numerator is going to be at least the same, if not higher. And it's a rational function. We don't have any square root, any radicals. So yeah, you can do long division or synthetic division. Which one do you guys want to try? Synthetic, okay.
Is that the one with the numbers and stuff?
Is that when yeah, but if you want to see long division, I can do it as well. We always, what number do we choose outside the box?
Is it for the negative?
Yeah, always change the sign, yeah. Okay, what number can we put in the first space here? Followed by,
Zero.
okay, followed by,
Zero, zero. And
Okay, so good. We have a placeholder for every degree that's represented: x cubed, x squared, x, and the constant. Okay. All right, we'll bring the first number down. Multiply with the outside. Bring that number down. Multiply with the outside. Okay, so what does this degree start with? Good, good. We start, our original numerator was x cubed. We know we're dividing by x to the first power, so all of our degrees will drop by 1. And the last one is remainder. So we basically now have a new problem to solve, but it should be a lot easier. It should be a collection of power rule and then a U substitution. Okay, first term, power rule. All the first 3 terms are all power rule. What about the last term?
That's, U substitution.
Yeah, U substitution. What's our U value? Do you know the shortcut to this? Can you jump directly to the integral rule?
Natural log,
Mhm.
so that would be
So if you're comfortable, you can jump directly from here to the natural log rule. I'll work out the full steps.
Well, then we have to plug in the other.
The bounds, right? So no plus C, but let me just do the work for this here.
Mr. Yang, why is there no plus C?
Because it's a definite integral, so we're gonna have to work in the bounds. And if we work in the bounds, the C's will just end up canceling each other out.
Okay, thank you.
Yeah. Okay, so that's where that negative 21 natural log of x plus 2 came from if you want to go through the full U substitution. Okay, so no plus C. Let me rewrite this. Okay, everything's in terms of x. We don't have to do any sort of adjusting with our bounds because everything's in terms of x. So again, no plus C. Okay, what do we plug in first? Yeah, upper bound first. Yeah, upper bound gets plugged in first. Big minus sign, big parentheses, and now repeat the process for the 1. Okay, I'm not going to require you to simplify. If you can get to this point, this is acceptable. Same thing on the AP exam.
Or you just plug it into the calculator.
Yeah, you can plug in the calculator as well, but I want to see your steps. I want to see you get from here to here. If you want to use your calculator to reduce it down to a number, that's fine, but I need to see from here to here.
Is this one where there's 2 methods for it?
Yeah, there's 2 methods, but we skipped the U substitution mainly. If this was in terms of U, we may adjust the balance, but you see how none of these terms are U substitution, so I would just get everything in terms of X. I wouldn't do the other method because we have mix of X and U's, so.
Would there ever be a time where the other part would have U substitution?
Oh, for these problems, no. For these problems, we don't. The U substitution is just a very minor portion. Something like number 4. Number 4, if this was definite integrals, then you can go through the adjusting the bounds in terms of U, or you can bring it in terms of X here. So this will be a good candidate for having, choosing between two methods. Well, I'm giving you that option, right? You can either do it in terms of U, or you can bring it in terms of X. I'm giving you that option. You don't have to do it the U method. Oh, that just means, let's say the bounds were from 1 to 4. Then you can use these original bounds with your expression in terms of X. There's no need to adjust the bounds. But if you wanted to find if you wanted to evaluate the bounds at this stage, then you have to change the bounds to be in terms of U, plug it into in terms of U here.
Put the 1 and the 4 and the X's and get the U value.
Right, these are not U values. So if you want to evaluate the antiderivative using this expression, then the bounds have to match. You got to push it through here. But I know most students prefer this method, which is fine, right?
I'm lost on the other part.
Oh, the U portion.
Using the U, like I'm confused.
Okay, so I can show that
I'm
to
so
you,
used to the other ones.
which is fine. But I do want you to be familiar with this method. Sometimes on the AP exam, they're forcing that situation. So let's say we have this -2 over U, right? Let's say we stopped here.
So if you were to evaluate the bounds, you would stop there before getting to the very end.
That's right. And let's say we want to evaluate -2 in U, but then the bounds were showing 1 and 4 in terms of X. So you'll plug 1 into the X's to get in terms of U. So if X equals 1, then U would be equal to e to the first power plus e to the -1. So that would go here. Now, this is not a very good example because, this one is just obvious that.
If it didn't have like e's in it, because that's kind of.
Right. If it doesn't have e's in it, then maybe it's a little bit cleaner going through this method, but at least I want to show you the method. So this is how you would do it. If X is equal to 4, then U must be equal to e to the 4th plus e to the -4. So then you put the results of your new upper bound.
And then you plug those into the U.
There we go. And then
Okay.
this would end up giving you the same result as if you did it in terms of X. But what a lot of students do is they stop here and they use the 1 and 4, and that's the biggest mistake.
In terms of X.
That's in terms of X, right? So that is the method that a lot of students want to do, which is not correct, right? So either you bring it in terms of X, or you stop at U and you convert the bounds in terms of U. We don't want to mix the X and U's. Okay, what time do we have here? 8:13. Okay, all right, so I have another help session this afternoon. We need to get ready for first period, so. All right, thanks everyone. See you guys in class.
Thank you.
Thank you.